Okay. Now consider the following compounds. And so with these 12 compounds, we get different structures. Draw the Lewis structures for each and predict the molecular structure. And predict the bond angles and polarity. Okay, so for CO2, so we get 4 from carbon, so counting out valence, 6 times 2 equals 12 from oxygen, so 16 valence electrons. So this guy is going to be our typical oxygen with a double bond to carbon and each of the oxygens, so we get our full octet. If we count, we have 2, 4, 6, 8, 10, 12, 14, 16 valence electrons, so that looks good. So then this is our molecular structure, which is linear. And although there are dipoles from oxygen to carbon, they will cancel, and so it's non-polar. And our bond angle is 180 degrees. So for our next one, SO2, so now we have 5 valence and 6 times 2 for oxygen, which is 12, so 17. Now if we try to draw similarly, so we're going to get a double bond to sulfur, but then we're actually only going to be able to form a single bond to the oxygen and then hold a lone pair on this sulfur. And actually sulfur has 6 valence electrons, sorry, so there should be 18. I got carried away a bit there. And so now everything is a full octet, but we have a -1 charge on the oxygen and a +1 charge on the sulfur. But we also have resonance structures. And then due to the lone pair here, we're actually going to get a trigonal planar electron geometry. So writing this as a molecular geometry. It would be more like this, so a bent shape. We definitely have a dipole along this direction, but of course, because of the resonance structures, this charge is actually being shared. Giving us a dipole along both bonds, and that's too many electrons. And if you recall, a resonance structure doesn't mean that it bounces back and forth between the two, but it's actually a superposition or an average of the two structures, meaning that the real structure is something more like this. With partial negative charges on these two and a definite positive charge on the sulfur, meaning we have dipoles in these directions and so a net dipole in this direction. And because of the lone pair, this bond angle will be less than 120 degrees. The molecular structure is bent and it will be polar. Okay. KrF2. So krypton is a noble gas, so we'll have 8 valence here, These are both halogens, so 7 times 2 equals 14. For krypton to form any bonds at all, we're going to have to move its some of its electrons, but we can do that. So krypton will at least have to do it this way. So split a pair of electrons, which we can do as we move into the D block. And so that will give us our bond there with 3 lone pairs on krypton. And so then if we draw our molecular structure, so there would be a lone pair here, a lone pair here, a lone pair here, and then fluorine, and fluorine. And so this is actually a linear molecule. Our bond angle is 180 degrees. And although there would be dipoles, they will cancel, so it's non-polar. Okay. Sorry. SO3. So we have 6 valence from our sulfur, and 6 times 3 equals 18 from our oxygens, so 24 total. We're going to need to have 3 bonding partners here. So our sulfur is going to need to have 3 electrons available. So we're fairly certain that to get an octet, we're going to have to do something like this. So I'm drawing 2 little electrons there now. I'm going to go ahead and pop that on this oxygen here, just kind of as a shortcut. But then we're still going to have trouble getting our octet. So that guy would have a -1 charge, which means the only way that we're going to be able to make this happy then is for this to actually form a double bond here and here with these guys. Okay, so then we're going to actually have something more like this. Where that's negatively charged, that's positively charged, and these two are neutral. But that looks pretty good. And it's going to be a trigonal planar structure because it's only bound to 3 species. And so then we're going to have something like this. Okay, with a negative charge here and a positive here. But of course we have resonance structures. And so in reality, the charge is shared around the ring. And the real structure is going to be something in between. Similar to this, where we now have a positive charge definitely on the sulfur, and the negative charges are shared around. So what that means is that we've got a perfect 120 degrees in here, and the dipoles will all directly cancel, meaning this guy will be non-polar. And it'll be a trigonoplanar structure. Okay. I might have to pick this up later. Okay, let's see what I can do here. NF3. So for NF3, we've got 5 valence here. 7 times 3 equals 21. So 26 total. So our nitrogen typically has 5. Our fluorines like this. And so this is actually a nice normal structure, or one that we're used to. Drawing this as a molecular structure. With wedges to show it's coming out of the page, and dashes for into the page. So we've got a trigonal pyramidal structure. And then these angles are less than 109.5 degrees because the lone pair has kind of squished them down. There will be dipole moments between each of these, and they won't cancel, so there will be a net dipole upward, and so this guy will be polar. Alright, IF3. So IF3, we've got 7 here. 7 times 3 equals 21, so 28 total. Our iodine, just to skip some steps here, is going to need to have 3 available for bonding, which means its other 4 electrons are going to be in lone pairs. So it must have split one of the lone pairs for bonding. Okay. And so then if we draw our molecular structure here, then we're going to have iodine. Our lone pairs are going to be at the side. And this. Now these are, because of the lone pairs, are going to be less than 90 degrees, as it's going to squeeze it down. And this bond angle is going to be less than 180. There will be a net dipole towards the fluorines. These two will cancel, but there will be a net dipole that won't cancel here. So this will be polar. And the molecular structure is T-shaped. Okay, CF4. So for carbon, we have 4 valence. Each of the fluorines has 7, which is 28 total from the fluorines. So the total is 32. And here again, we have something more akin to what we're used to. Where these guys should all bond together. And so this is going to give us our tetrahedral CF4 solution, our tetrahedral CF4 structure. Okay, so these are all 109.5 degrees, tetrahedral. And although there are bond dipoles along each of these, because of the symmetry, they will cancel, so this guy is non-polar. Okay. SF4. So here we have 6, and 7 times 4 is 28 for a total of 34. Our sulfur is going to need to form 4 bonding partners. It normally has 6, so it's going to just keep a lone pair. Okay. So this guy is going to be something like this. Where that's going into the page, and I have this lone pair coming out of the page. And so this is a seesaw structure. It will be polar due to non-cancellation of our dipoles. And these angles, because of the lone pair here, will be less than 90 in here. So everything will be squished together a little bit. And yeah. Okay. And then xenon F4. So we've got 8 valence there. 7 times 4 equals 28. So for a total of 36. Our xenon is going to need to have 4 bonding partners, but it has an extra couple electrons, so I'll just plunk them there. And like this, so we've got our bonds. And so then our molecular structure. So I'm going to put the lone pairs below and above, and I'm going to draw these coming out of the page, going into the page, coming out of the page, and going into the page. And then each of these angles in here is going to be our 90 degrees. This is a square planar structure. And although we have dipoles in here because of the symmetry, this guy is going to be non-polar. Okay, now PF5. So phosphorus has 5 valence electrons. Each of these contributes 7 for 35. And a total of 40. So for PF5 to have 5 bonding partners, all 5 of its valence electrons must be split. Okay. And here we go. And so then we would have a structure like this, where those are out of the page. Okay, and so then although there's dipoles in here, they would all cancel. And so this guy's non-polar. That's a 90-degree angle. These are 120-degree angles. And the structure is trigonal bipyramidal. Okay, and a couple more. IF5. So here we have 7. Here we have 5 times 7, which is 35, for a total of 42. So iodine needs to have 5 bonding partners, and then it's going to have a lone pair. And just sprinkling these around. So these are all going to bond nicely. And so we've got iodine with, draw this, okay. Lone pair up above, fluorine coming down, and then these are coming out of the page, going into the page, coming out of the page, going into the page. And so these angles here are going to be less than 90 because the lone pair is going to squish them, and these here are also going to be less than 90. There will be a dipole towards the iodine, which, because of the deviation from a symmetric structure, is going to lead to a net dipole. So this will be polar. And then for our last molecule here, SCl6. So sulfur has 6 valence. Each of these contributes 7 times 6, which is 42. So then in total it's 48 electrons. Each of sulfur's 6 electrons must be available for bonding to bond to 6 partners. Okay. And so it must be something like this, which if we draw it would be each of these going this way, coming out of the page, going into the page, coming out of the page, going into the page. And so this is an octahedral structure. Each of these angles is 90 degrees. And although each of these bonds would be polar, there's perfect cancellation, so this will be non-polar. Okay. So that's all of them. So going, I lost it. Okay, going back to the top here, we have CO2, which is linear, bond angle of 180, and it'll be non-polar. SO2, which is bent or V-shaped, and it will be polar. And the angle will be less than 120. KrF2 is linear with a bond angle of 180, and it will be non-polar. SO3 will be a trigonoplanar structure, which is non-polar because of the cancellation, and a bond angle of 120. NF3 is going to be pyramidal or trigonal pyramidal, bond angle of less than 110, so about 107, and it will be polar. IF3 is a T-shaped molecule with 90 degrees in here and 180 degrees from the fluorines, and it's polar because of its lack of symmetry. CF4 will be tetrahedral with angles of 109.5, and it's non-polar because of symmetry. SF4 will be a seesaw shape. and it will be polar. And the angles will deviate from ideal conditions due to the lone pair. XeF4 is square planar. All the angles are 90 degrees, and it will be non-polar because of the symmetry. PF5 will be trigonal bipyramidal with angles of 90 degrees here and 120 degrees on the equatorial. And it will be non-polar. IF5 is square pyramidal, and it will be polar, and bond angles will be less than 90. And SF6 is all the angles will be 90. It's an octahedral structure, and it will be non-polar. So that looks good. All right, and I'm actually going to stop this here and say thank you all for watching. I hope you enjoyed this. If you did, please subscribe to OneClass. If you want to leave questions, please follow the links below the video. My name is Jeff Kraus, and I hope to